Okay, good morning, everyone. So in today's lectures, we are going to talk about explicit Runge-Kutta methods. So you see that, the idea is YT1 can be approximated by a quadrature, okay, of this form. So remember, in the Euler method, you use only 1 point, okay? Trapezoidal method, you use 2 points, but in general, you can use more than 2 points, right? So you can use up to new points. And then, you design a quadrature, this sum, so that your method will have the order conversion will be like OH to some power, power 2, power 3, and so on. Yeah, so then in this form, then Y1 is defined by this formula. And in general, the Runge-Kutta method, the explicit Runge-Kutta method of new stages, okay? So new is the number of points in the quadrature, can be written in a general form like this, okay? And so where does the coefficient A21, A3, A31, A32, and so on come from? Or so C1, C2 up to C new, where does it come from? Well, so remember, it comes from, you solving a nonlinear equations that make the local truncation errors of order OH to some power. Remember, so this is like before we had a Runge-Kutta method of order 2, right? So of this form. And you make the local truncation errors going down of the order OH square, right? So you have to solve those 3 equations, okay? And because you have 4 unknowns, but 3 equations, so you can have more than 1 solution, yeah? So the Runge-Kutta method of order new is you have to solve, like new equations or more than that, and then you get out those coefficients. And right now we are not going to derive those equations for Runge-Kutta method order 4, but you get the idea, right? And we just study how to apply those equations. And now, for example, so this is the general form, okay? So in the past exam papers, you can see that the general form of the Runge-Kutta method are given, and then the table are given, and you are asked to write down what is the formula for the Runge-Kutta method of some order. So for example, we take one table like this, okay? So remember, so the table has the form CAB, yeah? CAB, a cap for taxi, yeah? So C is the column vectors here, B transpose is this row vectors here, and the matrix A is here. So empty means 0, 0, and this one A21 is just 1/2, and this one equals 0. So let's see how do we write down the equation for, say, the first table. Well, let me write down, for example, the first table. I share my piece of paper, and so you can see that for the first table you have, actually this one is similar to the lab problem yesterday, okay? But anyway, we can write down again, okay? So 0 and 1, right? And then you just, so here there is two rows, so you have new equal 2, yeah? And you got xi1 equal yn, xi2 equal yn plus h over 2. So h over 2 come from here, from this number, okay? F of Tn xi1, and then that's it. And then you have yn plus 1 equal yn plus, so B0 is 0, so we have only B1, so B1 is 1, so 1 times H, then F Tn xi 2. And do not forget to add, so this one is C1, this one C2, so do not forget to add C1. So C1 is 0, but C2, H over 2 here, okay? So then this one gives you the Runge-Kutta method of order 2, so RK2, with respect to this case, with respect to this table, okay? And you can do the same for, suppose I have another table of order 3. Okay, so this one is in the lecture. So go back to the lectures. Yeah. So suppose I have a table of Runge-Kutta method order 3. Okay. Well, so remember those numbers come from, you know, the solution of those 3 nonlinear equations. Sorry, 4 nonlinear equations. Okay, so we do not solve it, but we assume that we have a solution. And now, how do you convert this into a formula? And once you have the formula, you can put in MATLAB, right? So, okay, so now let me try to write down the formula for the second table. So now this is my RK3, yeah? So RK3. So remember here we have nu equal 3. Yeah? And then you have xi1, xi2, xi3. So xi1 is just yn, xi2 is just yn plus h over 2 f tn xi1. So where do I get h over 2? Well, this number, right? So this number gives me the coefficient here. Okay. And then xi3 is yn plus. Okay, so this is a minus. Yeah. So I have a minus and minus h over, well, just h, yeah, because there's nothing here. So f of question. Yes, it's correct. In this case, then A is a 3 by 3 matrix. And when it's empty, then it means that it equals 0. So when I don't write anything, it just means it equals 0. Okay. Yes, correct. So in general, A is a nu by nu matrix. Nu is the number of stages. Okay. And then this one gives you the coefficient for the term with respect to xi1. Okay. So we continue with this, yeah. So now, so minus 1, so that this minus 1 give you this formula, yeah. So Tn xi1, yeah, and then plus 2, right? Because now you have 2 hf Tn xi2. And now, because remember it's xi2, so you have to add on C2H. So what is H over 2 here? Yeah. And that's it. And then now you have yn plus 1. So yn plus 1 will be yn plus now B1. So B1 will be H over 6 f of Tn xi1 plus B2. So 2/3. So 2H over 3 f of Tn xi2, right? And do not forget the h over 2 here. Okay. And the last term will be h over 6 f of Tn, and do not forget the C3 here, so plus h psi 3, okay? And this is your RK3 methods. So once you have those formulas, you just need to put it in MATLAB in the correct form, and then you have the method, okay? And so the next one will be RK4. So if you go to the lecture note, you will see the table for RK4. So now suppose I go to the lecture notes. Well, so this one is another table of third order Runge-Kutta method, because remember here you have 4 equations, yeah, but you have how many unknowns? You have 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 unknowns. So you have, you know, like more freedom. You know, you have more than one solution. And okay, so now this is a 4th order Runge-Kutta method. So this one you will use it in the project, yeah. So how do you write out this? How do you write out this equation? So you first I copy down the table. One half one over 6, 1 over 3, 1 over 3, 1 over 6. Okay, so let me write down the equation. So now this is my RK4 table, right? So RK4 table. So you see that, okay, now the number of stages is 4, right? So you have xi1, xi2, xi3, xi4. So xi1 start with yn, yeah? For explicit method, xi1 is always start with yn. And then xi2 is yn plus, okay, so this 1/2 here, so you got h over 2 f of Tn xi1, yeah? And now xi3, okay, so 0 here, so it means that there's nothing for f of xi1, but this is h over 2 is something with f xi2, so you have to put h over 2 f of Tn xi2. But remember, because this is C2, right? So C1, C2, C3, C4. So C2 is non-zero. So h over 2. So you have to add h over 2 here. Okay. And then xi4, okay? So xi4 is yn. And so there's nothing with respect to xi1, nothing with respect to xi2. So you have 1 for xi3. So you have h f Tn xi3, yeah? And now do not forget the C3. So C3 is 1/2. So you have to put h over 2 here. So now you have 4 temporary variables, xi1 up to xi4. And now you just put in yn plus 1. So yn plus 1 is yn plus b1. So b1 is just, so this is my b1, yeah, b2, b3, b4, yeah. So h over 6 f of Tn xi1 plus h over 3 f of Tn xi2. And I have to move the camera a little bit. So do not forget the C2 is 1/2, so you have to put h over 2 here, and then plus, okay, so the term with respect to xi3. So you got B3 is 1/3. So you got h over 3f Tn xi3. And remember, C3 is 1/2, so you have to put h over 2 here. Okay, and the last term will be h over 6 f of Tn xi4, right? And remember the last C is 1, so you have to add h here. So if you don't put in the correct formula, then you don't have a correct method. And you don't have a correct order of conversion. Okay, so everything have to be very, very precise. Okay. So this is the method for you to work on the project, at least the explicit Runge-Kutta method of order 4. Okay. And now we go to the next method, what is, wow, so this one is just some notes about higher order explicit Runge-Kutta method. So you can go on up to 5, 6, 7, but it seems that Runge-Kutta method of order 4 is the most popular. Okay, so in MATLAB you see that ODE 4.5 implement the the combination between Runge-Kutta method of order 4 and order 5. Yeah, so they don't use higher order because it become a little bit cumbersome to have all the xi1 up to xi new. Yeah, and the next, well, so this one is an example of the Runge-Kutta method of order 2. So we wrote it down already. Yeah, so here you see that C1 is 0, C2 is 2/3. So you got nothing here and 2/3 here. Okay, so because of C1, and the B1 is 1/4, B2 is 3/4. So you got B1 is h over 4, B2 is 3h over 4. Yeah, and the 2/3, so the 2/3 comes here in the xi1 and xi2. Okay, and you can write down a little script. Well, we did it in the lab yesterday of the RK2 method with and you see that you can use that script or you can compute by hand, okay, to carry out 2 steps, so to see whether your method is correct. So you see, you compute this table in order to see whether you enter the formula correctly, because sometimes you have a small typos, then the method doesn't work. Okay, so you see this one compute explicitly at least in 2 steps. Yeah, so T0 equal 1, and then the method has step size 0.25. So you got this one is T1 is 1.25. You compute xi1 explicitly, xi2 explicitly, and then you compute yn plus 1 and so on. Okay. Okay, now implicit Runge-Kutta method. So remember before, in the explicit Runge-Kutta method, you have the sum run only from 1 to, sorry, this is explicit Runge-Kutta method. The sum run from 1 to j minus 1, right? So therefore your table has like a lower triangular format, but like in the implicit one, the sum will run from 1 to new. Okay, so your matrix is not lower triangular matrix, but it will be a full matrix. Okay, and then yn plus 1 is still defined the same. But now what is the drawback? So the drawback is you will see that every step you have to solve a nonlinear system. Okay, so now look for this example. So this one is implicit Runge-Kutta method of order 3. So you see that you have two rows. Yeah, so let's see whether we can write down the equation in this case. So now I copy down this table first, and then see whether we can write out the equation for this table. So 5/12, and you got 1/4, 3/4. So now we get out the piece of paper. So now you can see that my table look like this, yeah? Okay, so what is my xi1? So my xi1 will be, well, so you start with yn, yeah? And you have to add h/4 f of t1, sorry, tn xi1, yeah? Well, because c1, so this one c1 and c2. So c1 equals 0, so I don't have to add anything, yeah? Plus, or maybe minus, because there's a minus here. So minus h/4 f tn. Well, because now you have 2/3, so you have to add to h/3 xi2, okay? And now you got xi2 is yn, right? Plus h/4, well, so this is this h/4 come here, yeah? F of tn xi1 plus 5h/12 f of tn xi2. Well, we forgot the 2h/3, yeah? So we have to put 2h/3 here. So you got xi1 and xi2. So remember here you have got xi1 and xi2 on the left and on the right hand side. So every step you have to solve a system of two nonlinear equations, right? Because f here can be nonlinear, okay? And you know how to solve it already by fixed point iteration, by Newton methods, by bisection method, you know, by fsolve commands, you know. And then yn plus 1, okay? It's just yn plus, so this one is 1/4. You have h/4 f of tn xi1 plus 3h/4 f of tn plus 2h/3 xi2. You see? So once you solve the system, you got xi1, xi2, you just plug it in here, then you got yn plus 1. Okay? So that's exactly the slide here. So the slide here. So I just wrote down exactly this. So xi1, and you got yn, you got h/4 f of xi1 minus, so h/4 tn plus 2h/3 xi2 and so on. Okay, and then you got the last formula. So you see, why do people use implicit Runge-Kutta method? Well, because it will be more stable. So you will see it in the very last lectures. Okay, and you see that, you know, like when you have two rows for the explicit Runge-Kutta method, you just have order 2. But in this case, you can have order 3. Okay, in the sense that the errors will go down like OH to the 3. Okay, or it can go to up to order 2 new. So it means that, you know, for 2 rows you can have order 4, and that is exactly the one that you are going to use for the project. Okay, so maybe now we do a little exercise. Suppose I give you this table. How do you write down the system? So I put it on a Google Documents. See whether you can get out the so let me share my Moodle, yeah. So if you go to Moodle, you can see that interactive document. And the last one is Implicit Runge-Kutta method of order 4. Okay. So suppose I give you a table like this. How do you write down the formula? Okay, so this one is for your project. Yeah. So how do you write down the formula to compute yn plus 1? So what is your xi1 and what is your xi2? Just type it in here. So can you type it in? I can see it right now. Anyone? Yeah, so yn plus 1 is yn, yes, correct. Plus h over 2, yes. F of Tn yep, so 1/2 minus square root 3 over 6, yes, correct, yes. Xi1, yeah. And then h over 2 f of Tn plus h 1/2 plus square root 3 over 6, yeah. Xi2, yes, exactly. So how about Xi1 and Xi2? Yes, how about Xi1 and Xi2? Xi1 is yn plus h over 4, yeah, f of Tn yeah, 1/2 minus square root 3 over 6. Yeah. Xi1, yes, correct. Yeah. Yeah. Yes, f of Tn yeah. Okay, yeah. And then yeah, so make sure that you put in on the equation correctly. And then Xi2 yn yeah. So 1/4 yeah. So you got the idea, right? So now your job is to solve these nonlinear equations. And remember, in your case, in the project, Xi1 is a vector, it's a 3x1 vectors. Okay, so column vectors of 3 elements. And Xi2 is another vectors of 3 columns elements as well. So you need to solve it. You see, this one you can solve by fixed point iteration because you see on the left, you have Xi. On the right, you have a function of Xi, right? So you can solve it by F-solve or by fixed point iteration. Okay. So anyone got a project running, at least for the implicit Runge-Kutta method? Yeah, so you got the idea, right? So this is exactly what you need to do. Question? Good question. Initial guess, well, just make it 0 or 1, I don't know. I mean, It depends, but you know, I mean, if you use fsolve, I don't remember whether you have to supply the initial guess or not. But you know, just take a 0 or 1 random 6 numbers, random 6 integers, you know, and see how it goes. But I remember that you can choose some random guess. Okay. So any more questions? So the project could be done easily, right? So it can be done within next week. Yeah. Okay. So now we go back to the lectures. So now you see that we did the implicit Runge-Kutta method out of 4, and you can write down the method for implicit Runge-Kutta method order 3. So this table is for order 3. Okay. Question? No. You don't have to solve it by hand. So remember, you study fixed point iteration, right? Fixed point iteration, yeah. Or you can use fsolve. So this one is fsolve command is in the optimization toolbox. So you have to help fsolve. Okay. Otherwise, you just use fixed point iteration. So fixed help, yeah. fsolve. Okay. Yeah. So fsolve, I can show you the MATLAB for fsolve. Yeah. So if I go to fsolve. So let me show you the documentation for fsolve command. Yeah. So stop, share this. Okay. So fsolve, yeah, is the function that solve a system of nonlinear equations. And an example, so an example is like this. So suppose you have 2 nonlinear equations, yeah. Then first you have to define your nonlinear equation, you know. So maybe this is a function f, and this essentially give you f1, the first equation, the first nonlinear equation. F2 is the second nonlinear equation, yeah. And then you have to give some initial guess. So in this case, just give 0, 0. And you just solve fsolve, yeah. And then it gives you the 2 solution. Okay. But you see fsolve here, you have to check how accurate the solution can be. Because if you go to the you know, like the option, you will see that it can give you, you know, the tolerance of the solution, because this solution could be within like 10 to the minus 6 of the exact solution, but sometimes you need more accurate solution. Then you have to increase the accuracy by setting the correct options. Okay, I forgot the correct option, but you can look it up, yeah. So I believe that there is an option to improve the accuracy, maybe function tolerance, or you see, so this function tolerance, the default is only 10 to the minus 6, yeah. So you can improve the accuracy by decrease this number. or yeah, you have to look a little bit like more details how to improve this. Okay, otherwise you just use a fixed point iteration. Yeah, so you have to do some experiments with these commands to see how good the absolve command is. Yeah. So any question for this? Okay, so we go back to the ODE. Yeah. So this one is like another example of implicit Runge-Kutta method order 3, and now maybe we skip this, yeah, because you do the implicit Runge-Kutta method order 4 already. So now we move to a new topic, is a multi-step methods. So multi-step methods. So remember what we have studied: the Euler method, the trapezoidal method, the Horn's method, the explicit Runge-Kutta method, implicit Runge-Kutta methods. It computes yn plus 1 based on yn. Yeah, only single step. But the multi-step, it can compute yn plus 1 based on, more than that, more than just yn. So it can compute yn minus 1, yn minus 2, and so on. Yeah, so in general, it can compute from yk for k less than or equal n. Okay, then we call it a multi-step method. So remember, like midpoint method, okay, is defined by this formula. Then you see that this one, yn plus 1 can be defined from yn minus 1 and yn. Yeah, so this one is like two steps method already. Yeah, so it doesn't depend only yn, but it depends on yn minus 1 as well. So we will study only two families of multi-step methods. Okay, A, B, which stand for Adams-Basford methods. So they name after the mathematician who discovered them in the first place, or Adams-Newton methods, so our AM methods. So now let me introduce the general idea. Yeah, the general idea is, so we start with the fundamental theorem of calculus. So remember, we compute yn plus 1, yeah, is yn plus the integral from tn to tn plus 1 of the function f, right? Because remember, this one just y prime, yeah. Then, now instead of integral f, we will approximate f by a polynomial, by interpolating polynomials. Yeah. So maybe let me draw pictures to make it a bit like easier to understand. Yeah. So suppose I have a function, yeah, and this one is my Tn, or maybe this one say T0 and T1, so maybe Tn is here, yeah, and Tn plus 1 is here. Okay, and I'm interested in this point. Yeah, so this one will be my yn plus 1. I want to find out what is this value. Okay, and then, okay, so fundamental theorem of calculus say that yn plus 1 is just equal yn plus integral from tn to tn plus 1, okay, of f t YH. Okay, so YH is the approximate solution, yeah. DT. Okay. Yeah. So in general, you don't know the function y, right? So you have to approximate y by some YH. Yeah. So now you have some value before already. So you have yn here, yeah. So you have yn, you have say yn minus 1, yn minus 2, and so on. Okay, back to y1, yeah. So this one is known, and this one is not known. Okay. So now how do you approximate the integral? Well, so how do you approximate the function f? Then you can approximate the function f. Then you can approximate the integral, right? And remember, we studied the process of finding a polynomial that goes through those points. Yeah. So suppose I want a polynomial. Yeah. So I want a polynomial PR. Yeah. That go through those points. Yeah. So now I want PR. So R is just a parameter. Let we specify this. But suppose what I want is I want PRTN equal YN. Okay. And PRTN minus 1 equal YN minus 1. Yeah, and so on. Up to where? Up to where? Well, up to, I want to look back only up to Tn minus R. Okay. R could be 1, 2, 3, 4, 5, but let me just call it little r, yeah. And this one is yn minus r. Okay. So then what is the polynomial PR? So what is the polynomial PR? So the polynomial PR is just the interpolating polynomial that go through those points, yeah. So this one is, suppose I approximate go to 3 points, yeah. So then this one will be my P2, right? So because it go through only 3 points, yeah. Then after that I just let it go further, and I approximate that I approximate the integral of f by this integral of PR. Okay. So now my yn plus 1 will be defined to be yn plus integral Tn to Tn plus 1 of PR dt, yeah. Okay, so this one will be my multi-step method. So now the whole point is, what is PR? So the key point is, what is PR? Well, so remember you studied interpolation already, right? So PR could be just a Lagrange polynomials that go through those yn minus 1, yn minus 2, yn minus r points. Okay, so I can choose PR to be the Lagrange polynomials. Yeah. So if I choose PR to be the Lagrange polynomial, then I got PR. So remember now PR is just a function of t. Yeah. Then what I have is what? What is the polynomial? Well, because it goes through yn. So you got yn L of something, right? So So now maybe let me, no, actually, strictly speaking, we don't want PR equal yn because we don't integral the function y. We integral the function f of y. Yeah. So actually, what I want is this one is f of y n Tn. Yeah. Not the function y because we integral the function f. So I want to interpolate f, the function f, not the function y. Yeah? Okay. And so now my polynomial will be the f of yn. Yeah. And the Lagrangian will be Ln. Okay, plus f of yn minus 1, Lagrangian Ln minus 1, and so on, up to f of yn minus r, Lagrangian of n minus rt. Okay, and then you see, then your integral, because so this one is known, right? Because your yn you computed already, it's a numeric values of yn. So this one is known as well, the function f is known. So what you need to do is just compute the integral of the Ln, right? So because now if you integral this, yeah, then you need to know only the integral from Tn to Tn plus 1 of those Lagrangian. Okay, and then this give you the Adams-Moulton method. So that is the idea. So we go back to the slide and we make the calculation more precise. So now if I go back to the slide, okay, so I say that, okay, so now we have yn plus 1 equal yn plus the integral from Tn to Tn plus 1, yeah? And you approximate f by the polynomial PR, yeah? And PR Tn minus j equal f Tn minus j. So this one is just a shorthand notation for, you know, saying that it's an interpolation polynomial at Tn minus r, or up to Tn. So, yeah, so before we write down like at Tn minus 1 at Tn minus r. So just you can do a for loops. You can write out like this, yeah. Then the polynomial is just the Lagrange polynomials, yeah, in this form. And now the Lagrange interpolation polynomials. Okay, so remember this one is just the function with respect to t, just a one variable. And you can write down the formula for the Lagrangian. So t minus Tn minus I, and take the product of all those terms, I different from j, and then divided by, you know, the Tn minus j, Tn minus I different from j. So this one is the Lagrange interpolation polynomial with respect to the variable t. And then you need to integral those Lagrange polynomials. Okay. And you can see that, you know, if you make a transformation, okay, you let s to be t minus Tn over h, then this integral will reduce to integral from 0 to 1. Okay, and the function Lagrangian Ln minus j of t will be L star n minus j of s, and it's given by this formula. And this formula can be simplified to be this formula. Okay. So I leave it as an exercise for you to check it. Yeah. But you can check for a few cases, you know. So suppose I want to check. So look at the simple case. So if suppose you want to check for so what is the simple case? Suppose you have R equal so let we check like the simple case, yeah. So suppose you want one R equal 2, right? R equal 2. Yeah. Then if I go back to the formula, yeah, so I just have L of n t and then L of n minus 1 t, then L n minus 2 t, right? So remember J from 0 to R, yeah. So this one is the product of I from 0 to R. So R is equal to t minus t n minus I t n minus j t n minus I. Okay. So in this case, j just equals 0, right? So j equals 0, so you got 0 here, yeah. Okay, so this one will be, so it will be t, so I has the different from j, so I different from j equals 0, so this one is mean that j equals 0, yeah. So I different from 0, so then you cannot have I equals 0, right? Because I has the different from 0. So you got t minus t n minus 1, yeah. And then t minus t n minus 2, right? And this one is t well, tn, yeah. So you got tn minus tn minus 1, tn minus tn minus 2. Okay. And so on. So this one is, well, will be t n, well, so everything except tn minus 1. So it may be t minus tn, t minus tn minus 2 divided by tn minus 1 minus tn minus 1 minus tn minus 2. Okay. And the last one will be t minus tn, t minus tn minus 1 over tn minus 2 minus tn minus 2 minus tn. Okay, so the Lagrangian. And then the next step is how do you convert into L star of S? Okay, so the next step is, suppose I put S is t minus tn over h. Okay, then what happened to my ln s? So this one is j equals 0. So j equals 0. So before you got j equals 0, j equals 1, j equals 2. Yeah. So we do the same here. So j equals 0 is you got lns, yeah, equal well, so this one should be star, yeah. So okay, and so this one is defined to be ln of t, yeah. So now you put it in. So suppose I put in my ln of t in this line, yeah. Then I got so remember in this case, yeah, you make a transformation of variable. You have sh equal t minus tn. Okay, so therefore t equal sh plus tn, right? Yeah. So you move tn to the left. So this one will be ln of sh plus tn. Yeah. And then this is a function of h only. Yeah. So now how do I do that? Well, I plug it in. So ln, I just put in the parameters here. So instead of t, I put in sh plus tn minus tn minus 1 and this one sh plus tn minus 2 divided by sh plus tn minus 1 sh plus tn minus 2. So you see the last function, yeah, is no longer a function of t, but it's a function of h. Okay. And then you can integral. So now we have to worry about what is the integral. So we will worry about it later, but essentially that is the ideas, yeah. So if you go back to the slide, you know, it just explain that you know the LNS can be written in this form, yeah. So because we haven't simplified it, but when you simplify it, it will equal well, maybe we do one more step, and then you will see this, yeah. So if I do one more step, let me do one more step, yeah. So if I do one more step, you see that tn minus 1 is just equal h, yeah. So you got sh plus h, right? Because this one gives you h, yeah. So multiply sh plus, so tn minus 2, which is 2h. Okay. Then this one sh plus h, sh plus 2h. Okay, and you simplify h, and then it will become s plus 1, yeah, s2 over s plus 1 over s plus 2. Okay, so that is exactly the function we saw it here. You see, so it will be the form like this. So it's a product of s plus I over I minus j. Okay, so you can reduce to this form. Okay, and then after that, you know, you integral that number and you got out the methods. Okay, so this one is AB2, AB3, AB4. And so we stop here, yeah. So